In the last video, we looked at electron domain geometry, and that was the geometry based on electron domains. Remember, what is an electron domain? An electron domain was just simply a group of electrons. That could have been electrons that were in between bonded atoms, or that could have been unbonded, essentially lone pairs. When you think about electron domain geometry, they're just looking at electron domains, period. They're not looking at whether or not it's bonded or unbonded, because it includes everything. Molecular geometry, on the other hand, is only looking at atoms. In other words, it's only looking at the bonded pairs. Because if you think about it, it's the bonded atoms that actually are creating the shape of the molecule itself, not lone pairs of electrons. So in this video, we're going to look at molecular geometry and how it relates to electron domain geometry, because there is a connection, and you can't do molecular geometry until you do electron domain geometry. They build on each other, or I should say molecular geometry builds off of electron domain geometry. So let's go ahead and start taking a look at some examples. All right, here's the steps for determining the molecular geometry of a particular molecule. The first thing you have to do is you have to draw the Lewis structure. This is so important. A lot of times students want to just look at the formula of the compound or molecule and determine the geometry based off of that, and that is a mistake. You have to draw the Lewis structure because you need to figure out in step 2 how many electron domains are around the central atom. Remember, this is going to be either bonded pairs or lone pairs. Then, from the electron domains, you'll be able to, in step 3, determine the electron domain geometry. This was what we covered in the last video. Finally, once you know what the electron domain geometry is, you can then determine what the molecular geometry is. And like I said, the difference between 3 and 4 is going to be based on just the bonded atoms. All right, so let's go ahead and start taking a look at some examples. So let's consider 3 compounds. We have CH4, NH3, and H2O. The question's asking what are the electron domain geometries and then what are the molecular geometries. In order to figure out what's going on here, we need to go through our steps. And remember, the first step is you need to know what is the Lewis structure for each of those particular molecules. I went ahead and chose 3 really easy molecules so that way we can just focus on the geometry itself. All right, so I'm going to move this up just a little bit because we're going to need some space. All right, so let's go ahead and draw methane. Methane is just going to have this simple Lewis dot structure. And notice I'm just doing Lewis dot. I'm not doing anything with geometry. All right, so there's the Lewis structure for methane, CH4. The Lewis dot structure for ammonia, which is NH3, is going to look something like this. And then H2O is going to look something like this. And like I said, this is all review. You should know how to do these Lewis dot structures. Okay, so that's the first step. We did this first step for all 3 molecules, and that is you have to draw the Lewis dot structures. Okay, now right below, let me see if I can move this up. There we go. Okay, right below there, I'm going to do the second step. And the second step is how many electron domains are there. So if we take a look at the first one, methane, how many electron domains are around the carbon? Well, there's 1, 2, 3, and then 4. There's no lone pairs, so the total number of electron domains would be 4. All right, let's go ahead and take a look at ammonia. How many electron domains are there in NH3? There's 1, 2, 3, and then 4. Because remember, an electron domain is just a pair of electrons, regardless of whether they're bonded or whether they're lone pairs. So ammonia also has 4 electron domains. And then finally, let's take a look at water. Water has 1, 2, 3, and 4. So that's also going to be 4 electron domains. So now that we've done step 1, which is Lewis dot, and step 2, which is determining how many electron domains, we can now answer the first question: what are the electron domain geometries for all 3? Electron domain geometry strictly comes from how many electron domains there are. So since all 3 of these molecules have 4 electron domains, they're all 3 going to have the exact same electron domain geometry. And if you recall, 4 electron domains has the general form of AB4, and the name of that is tetrahedral. All right, so every single one of these is going to be a tetrahedral electron domain geometry. So if you remember from the previous video, you remember that tetrahedral had the central atom here in the middle, and then it had its 4 electron domains jutting off like that with 109.5 degrees. That's just some side information. But the point is, the electron domain geometry is just looking at, like I said, electron domains. We have no idea, looking at this right here, whether or not these are lone pairs of electrons or whether it's actually bonded to another atom. This is where the difference comes in between electron domain geometry and molecular geometry. So yes, it's true. All 3 molecules have the same electron domain geometry. That doesn't mean they're going to have the same molecular geometry, because molecular geometry just looks at the number of atoms, or excuse me, just looks at the atoms. So let's take a look at the first one. All right, CH4 had a Lewis dot structure shown, and it has 4 electron domains. Okay, of those 4 electron domains, how many of them are actually atoms? And the answer is all 4 of them. If you notice, all 4 electron domains are actually, they're bonded to hydrogen atoms. And so all 4 of these electron domains actually are atoms. When your number of electron domains is all atoms and none of them are lone pairs, the electron domain geometry name as well as the molecular geometry name is the same. And so the molecular geometry of the first one, CH4, actually is going to remain tetrahedral. So it actually does exist that this molecule, CH4, does have a tetrahedral shape. So notice the molecule actually would look like a tetrahedral because all of those electron domains are actually atoms. Okay, so let's take a look at the second example, which is NH3. All right, yes, it does have 4 electron domains, but of those 4 electron domains, how many of them are actually atoms? And the answer is 3. 1, 2, 3. The fourth one was that lone pair. So if you imagine the lone pair being up here, we don't really care about the lone pair because that's not actually going to contribute to the shape itself. It's an electron domain, and so it does have the electron domain geometry of tetrahedral. But of those 4, like I said, 3 of them are going to be the atoms. And so if you were to look at your sheet that is telling you all the geometry names, when you look at 4 electron domains, 3 of which are bonded, and 1 of which is a lone pair, so 3 and 1, that's actually going to have the name trigonal pyramidal. Trigonal or trigonal pyramidal. Notice it's not bipyramidal. This is actually the molecular geometry name, trigonal pyramidal. So what would that molecule actually look like geometrically? Well, here's what the molecule looks like with everything in place. Notice you've got the 3 hydrogens there, and then the 4th electron domain is the lone pair. But remember, for molecular geometry, we don't care about the lone pairs as far as what they contribute to the name of the molecule. So what I'm going to do is I'm actually just going to erase that lone pair there. And so it would end up looking something like this. I want to point out that the lone pair is important in the sense of it is repelling these 3 hydrogens. It's pushing them down. So they are still there. But when you just look at the molecule itself, we're only concerned about the actual bonded atoms themselves. And so notice that it's not a tetrahedral shape with the molecule. It's actually, we call it trigonal because it's got these 3 terminal atoms there. And then it's pyramidal because if you imagine, maybe if I draw it here, you can kind of imagine it's creating a pyramid shape. And so that's why it's called trigonal pyramidal. Okay, let's look at the last one, water. Okay, so you have 4 electron domains, but this time only 2 of them are actually atoms. The other 2 are lone pairs. So if I was drawing that out here, well, first of all, actually, I'm sorry. If you were to look at your sheet and you were to say, okay, of the 4 electron domains, 2 of them are bonded and 2 of them are lone pairs, what does that actually come out to be? The answer is that is the molecular shape of bent. So what does that mean? Like, why is it called bent? So if we draw, here's oxygen, here's the central. Okay, these 2 positions right here, here and here, that's going to be my lone pairs. Why? Just because I'm choosing to make those my lone pairs. Okay, so lone pair there and lone pair there, and then you've got your 1 hydrogen, and then you've got your 2nd hydrogen right there. But remember, we don't care about lone pairs when we look at just the molecule. So if I take those lone pairs out of there just for looking at the molecule, notice what you're left with. You're left with water actually having a bent shape. And so that's why a lot of times you see water drawn like this. I mean, it's the same thing. I'm just going to reorient it a little bit. They have water like that because water is actually a bent shape. And so notice all three of these molecules had the same electron domain geometry. They all had tetrahedral structure or tetrahedral orientation. But when you just look at the atoms, that's actually where you get the molecular geometries, and you can see the shapes of those molecules and how they differ. All right, so let's do some practice here. I'm going to pause the video just so it doesn't take so long, but here's what I want to figure out. I want you to take some time, and I want you to look at these two molecules here. I want you to, for each of them, determine what the electron domain geometry and what the molecular geometry is for these two molecules. So go ahead and pause the video, and then go ahead and hit play to reveal the answers. All right, so here's the answers for these two. First thing, notice what I did was for each molecule I had to draw the Lewis dot structure. I apologize that this one's a little messy. But then once I have the Lewis dot structure, I'm able to figure out what's the electron domain geometry, which is in blue, and what's the molecular geometry, which is in red. Now I want to point out real quickly, if you were to just look at these formulas, you probably would have gotten your geometries wrong. Because like I said, a lot of times students, they don't want to draw the Lewis structure. They want to go straight from formula to the shape. And that's not correct. You cannot do that. Because if you do that, you're not going to know that, oh, look, there's lone pairs on the central. There's no way you would know there's lone pairs if you don't draw the Lewis dot. And lone pairs do dictate your geometry. So you have to draw the Lewis dot structure. It's so important. So SO2, you may have put linear, and XEF4, you may have put tetrahedral. And as you can see, those are not correct. SO2 actually has 3 electron domains. That makes it trigonal planar, 2 of which are bonded, which makes it molecular geometry bent. For XEF4, it has 1, 2, 3, 4, 5, 6 electron domains, making the electron domain geometry octahedral. And of those 6, 4 of them are bonded, and that makes the molecular geometry square planar. Now lastly, I just want to cover real quick how the geometry changes if there are lone pairs of electrons on the central. This goes right back to the video before where we talk about electron domain geometry. Recall that every electron domain geometry, remember there's 5, linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral, have bond angles. They have angles associated with them. If there are lone pairs of electrons on the central atom, basically what that means is lone pairs are going to repel more. Why? Because these pairs of electrons are not bonded, meaning they're going to experience less nuclear attraction. So what does that mean for us? That basically means the bond angles are not going to be ideal. They're actually going to be slightly off from what we would consider ideal. And I'll go through that in a second. Double and triple bonds we find also repel more, and that's just due to the fact that it has higher electron density in that area. Remember, a single bond is only 2 electrons, but a double and triple bond are going to be 4 and 6 electrons, respectively. So let's take a look at what that would do to a particular molecule. So let's go back to the ammonia and the water example. Remember that we discovered that both of these had 4 electron domains, which meant their electron domain geometry were both tetrahedral. And I'm just going to write tetra. Don't write tetra for you. I'm just, for the sake of the video and time, I'm just writing tetra. Okay, so if you recall back from the previous video, what was the bond angle for a tetrahedral? And that was 109.5 degrees. All right. Now, that's 109.5 degrees, assuming that all the electron domains are bonded. But as you can see, one of the electron domains here is a lone pair, and 2 of the electron domains here are lone pairs. Don't worry about the bubbles versus non-bubbles. It's just different ways of drawing it. The idea is there's lone pairs. Because these lone pairs of electrons are not bonded, they're going to repel more. So remember, ideally, the angle between these hydrogens here, for example, they're going to be 109.5 degrees. But what happens is, because of this lone pair up here, it actually pushes these 3 hydrogens down further. And so these hydrogens actually are going to get closer together. And so what is the bond angle? Well, you don't really need to know what the bond angle is exactly. All you need to know is that the bond angle is going to be less than 109.5 degrees because these hydrogens actually get smushed closer together. So the bond angle is going to be less than. Same thing here. These two lone pairs are going to really push these hydrogens closer together. And so that means the bond angle between these two hydrogens is not 109.5. It's definitely less than 109.5. Now, what are they specifically? Well, just for your information, over here, these hydrogens that are in ammonia, they're actually about 107 degrees. And then the hydrogens here in water are about 105 degrees. Do you need to know that? No. But just for your information. The main thing is that the hydrogens get pushed closer together. Here's some other examples just so you can see it. Notice here on the left, this is a trigonal planar. So normally a trigonal planar molecule would be 120 degrees, but notice because of this double bond, it actually pushes these hydrogens closer together. And so notice the angle is slightly less than 120. You don't need to know that it's 116. You just need to know that it's less than 120. Now, for this level of chemistry, the only thing we're going to look at for changing the bond angle is lone pairs. So don't worry about double bonds and triple bonds. You're only going to look at lone pairs. So in these pictures over here, you don't see it drawn, but the lone pairs are actually existing right here. And so notice it changes the bond angle. For example, this bond angle should be 180. It's slightly less than that. These bond angles right here are also going to be smushed closer together because of how it's structured. This should be 120, and it's not. It's 101.5. Over here, this is octahedral because the sixth electron domain is a lone pair that's not shown. But notice the bond angles are not 90 degrees. There's something less than that because this lone pair that's not drawn here is what's pushing all these fluorons closer together. Like I said, you don't need to memorize specifics. You just need to know, oh, it's less than because it has a lone pair. It's smushing the atoms closer together. Finally, a quick note. What happens when you're dealing with a molecule that has multiple central atoms, which honestly that's the bulk of chemistry. There's very, very rarely do you deal with a molecule that only has one central atom. Basically, what you do is you employ the exact same things we've learned to every central atom. So if we're looking at this molecule right here, okay, it actually has three central atoms. There's this carbon, and then there's this oxygen. So there's three central atoms here. And so basically what you're going to do is you're going to employ the same things. So take a look at the first central atom, which, like I said, is this carbon right here. How many electron domains are there? There's 1, 2, 3, and 4. So that would be tetrahedral electron domain geometry. And of those four, all four of them are bonded to atoms. And so notice over here, this is the carbon. You can see that tetrahedral shape there. Now, when you get to the second central atom, which is this carbon, how many electron domains are there? There's 1, 2, 3. So even though it's drawn this way, this actually would have a trigonal planar look about it. And you can see that represented right here. You can see that trigonal planar shape. That's right there. And then finally, if you look at this central atom here, this oxygen, okay, you say, all right, how many electron domains are there? There's 1, 2, 3, and 4, which is tetrahedral. But of those four, only 2 of them are actually bonded to atoms. The other 2 are lone pairs. So you say, okay, 4 electron domains, 2 are bonded, 2 are lone pairs. That's going to be a bent structure. And notice in the picture that's on the right, that actually is what you see. You see like a bent structure that's right there. So you're basically just combining everything in chunks and pieces, and it kind of gives you the idea of what the molecule is going to look like overall.